Hello YouTube! Today we're going to be talking about things that aren't moving. So ideally you should be able to model how things that aren't move don't move. So how's that for a sentence? If you can choose a good pivot point, that is an excellent start, and basically if you can find out which forces need to be the same size as each other, you're in really good shape. A lot of times the AP exam will have questions like this structured as, if this force gets bigger, which other force must get bigger? I've seen that about 3 times in the multiple choice, which isn't a lot given that I've seen 8 multiple choice tests, but there aren't going to be a lot of questions on statics specifically. There might be one, and it might be an open response question, but there won't be like 5 of them. So the basic premise is, if something is at rest and staying at rest, then that means it's not moving, and it stays that way. If your velocity is constant, and in this case constantly 0, that means your acceleration is 0. If your acceleration is 0 by Newton's second law, your net force must be 0. So if something's not moving, the net force must be 0, and you can think of that as saying all the forces are balanced. So let me actually add that. That doesn't mean all the forces are the same size as each other. It doesn't mean that there are only, I don't know what else people think it means, but it does mean that they all add up to 0 or they're balanced. So what that tells you is you can set up an equation where you're like, okay, well, Fn plus mg minus the force of the person pushing it into the ceiling, because that's the situation I accidentally created, needs to equal 0. The same logic applies to rotation, though. If it's not spinning and it stays that way, that means that the angular acceleration must equal 0. If the angular acceleration equals 0, that means that the net torque has to be 0, which means that in addition to all the forces being balanced, those forces times r times f times sine theta must also be balanced. So what's interesting about this, one sec. Does balanced have one L and I keep messing that up? I just want everything to have a parallel. Yeah, it's one L. Oh wow, that was loud. Thank you. I just want everything to have the parallel line symbol in it, and so everything should have 2 L's. So we know that our torque is balanced, which means that we can basically set up, okay, well, torque 1 minus torque 2 plus torque 3 will need to equal 0. Which also means that R1, F1, dot, dot, dot needs to equal 0. We can plug in the R's and the F's and the sine thetas and have those equal 0. So this gives us 2 equations using force. Honestly, please. 2 equations using force, because there's the one with force and there's the one with torque. The weird part about this, the especially weird part about this that allows there to be some flexibility and creativity in how you solve these problems, is that if it's not spinning, then yes, it's not spinning around one end, but it's also not spinning around the middle. It's also not spinning around like another random spot in the universe. It's just not spinning at all. So you can put the pivot anywhere that you want, and it still has to work. I think all of this will become a lot easier to understand why this is useful or how to do it with an example. So let's just do an example. A ladder is leaning up against a wall. Identify all the forces on the ladder. Which forces must be the same size as each other? So here's my ladder, here's my wall, here's the floor. Let's just start listing out forces. First one, really easy. What force has to be on this ladder? I don't think that would look particularly different. First force that's got to be on the ladder. Easy one. Gravity. Gravity always comes from the center of mass, so effectively straight from the middle. Oh, I just realized that we probably should have learned about how to figure out where center of mass is for an object instead of just for like the... I don't care. We don't have time. All right, there are 4 other forces on this ladder. Normal, absolutely. Normal is anytime that things are trying to go through each other, you need a normal force. So which things are trying to go through each other? The wall on the ladder, yep. So the wall is going to put a normal force on the ladder. So I'm going to label that as the normal force from the wall. And then the floor, or the ground, absolutely. So I'm going to do normal force from the floor. All right, 2 more forces. What else is the ladder trying to do? It's not just trying to go through the floor, it's also trying to slide against the floor. So to stop it from sliding, there has to be some friction. Another way you can think about that actually is if we look at our free body diagram so far, because I've been drawing this picture as where all the forces are, but I haven't been drawing the free body diagram, we're going to need both. Our free body diagram so far has mg going down. It has the normal force from the floor going up, and it has the normal force from the wall going to the left. This thing can't be at rest. These forces can't be balanced. There has to be something pushing it to the right. So if I come back over here and add that in, I just realized I shouldn't use red. The floor needs to be pushing the ladder to the right to stop it from sliding to the left. So there's some force of friction from the floor. But the ladder is also trying to slide down the wall. So the wall is going to be pushing the ladder up. So adding that to my free body diagram, we'll have the force of friction from the wall going up. We'll have the force of friction from the ladder, from the floor going to the right. So, the next part is to think about which of these forces have to be balanced with each other. The free body diagram gives us an easy 2. The force of friction from the floor and the normal force from the wall must be balanced with each other because otherwise it'll move to the right or left. If that's not happening, they have to be the same. If we wanted to, we could also say that these sets have to be balanced with each other. So this is basically just setting up an x and y equation for our net force, except we're skipping a step and skipping straight to things that need to be balanced, instead of saying minus each other equals 0. We can also think about it, yeah, absolutely. We can also think about it with our torques. The weird part about thinking about it with torque is you get to pick where you put the pivot. If I think about the fact that this thing isn't spinning around the middle, I don't have to care about gravity for torque, because gravity doesn't make any torque around that pivot because gravity is pulling it from that pivot. And anytime you pull something from a pivot, you're effectively not generating any torque. The other place that we could put it that would make sense would be down at the bottom. If we put it down at the bottom, we can ignore the torque from the floor. because it's not spinning around that point. When we do that, suddenly we have to start caring about the torque from gravity again. And we have to start caring about the torque from the wall. Similarly, if we put it at the wall, the opposite happens. We care about gravity, we care about the floor, we don't care about the wall. Depending on what the question is asking you about, it's easier or harder to solve based on where you put the pivot. In this case, I do actually briefly want to think about which ones need to be balanced based on torque if we put the pivot here, because it's a kind of weird result. If I think about the direction that this normal force is trying to make it spin around this pivot, the normal force is trying to make it spin like this. The friction from the wall is actually doing the same thing. If I look down here, the friction from the floor is also doing the same thing. And if I look over here, the only force that's trying to stop it from spinning in that direction is the normal force from the floor. So that means that the torque from the normal force from the floor needs to be balanced with the torque from the other three, which is kind of weird. It means that that one in particular has to be bigger than the others by a pretty substantial amount. Plus the torque from the friction from the wall, plus the torque from the friction from the floor. If you wanted to take it one step further, you could go ahead and plug in RF sine theta. So that would tell you that now the thetas are going to be weird and they'll be based on the theta for the wall. I'm actually not going to get into the thetas of it other than to say that they exist. But R, which is 1/2 of the ladder length, so 1/2 L times the normal force from the floor needs to equal 1/2 L times the normal force from the wall times sine theta. These are all times sine theta with different thetas. Plus, and you do it for the other ones as well. You wouldn't have to solve out a problem with these. This was literally a problem on the AP exam a couple years ago and might show up on your rotation testy duder. I just don't remember. Yeah. Mm-hmm. Yeah. So mm-hmm. Yep. This one's probably easier to show than it is to explain. If I take this rod and I push it this way, watch which way it spins. If I take this rod and I push it up, watch which way it spins. If I go bring my hand to the other side and I push it up, watch which way it spins. And then if I go bring my hand to the other side and I push it the direction that friction is pushing it, watch which way it spins. So all three of those forces are trying to get it to accelerate angularly in this direction. The only one that's trying to get it to accelerate angularly in the other way is the normal force from the floor. And if it helps, you can literally just like take your arm and push it to see which way it tries to rotate to figure out which direction the torques should go and if they're with each other or against each other. That's it. Tomorrow we'll talk about a second example where you actually have to do some calculations. Hope you have a great day. I'll see you then.